Kako dizajnirati elektroniku za svemirske letjelice koja može da izdrži zračenje u kosmosu? Od kakvih materijala je najbolje napraviti odjeću za kosmonaute na dugim svemirskim misijama? Može li se od pijeska na površini mjeseca graditi baza otporna na kosmičku radijaciju? Kako ublažiti zdravstvene opasnosti kojima su izloženi astronauti tokom boravka u svemiru? Od odgovora koje će nauka dati na sva ova i slična pitanja zavisi tok i uspjeh mnogih svemirskih misija. Na planeti Zemlji postoje 2 naučna istraživačka centra u kojima se istražuju ove intrigantne teme. U Sjedinjenim Državama partner NASA je nacionalna laboratorija Brookhaven u New Yorku. U Evropi partner ESE je centar za istraživanja teških jona u Darmstadtu.
The same radiation that we use here for treating the tumor are very similar to the radiation that we can find in space and will eventually harm the astronauts. This is the reason why we are carrying a lot of projects for space radiation protection, and we have many projects also with ESA, and we are one of the ground facility of ESA. We work for shielding studies mostly, but also electronic studies, both for space travel, but also for in situ protection. With the time, it's growing more and more the interest of making a very long mission and eventually also a permanent space station on the moon. But when the astronauts will need to go to the moon, will need to be able to stay on the moon for a very long time, and this becomes crucial to properly protect them from radiation and be sure the radiation won't be harming them. To do this, we do a lot of studies since looking for different materials and techniques to allow astronauts to persist in space for longer and longer time. One of these is the idea of proper building a moon habitat. For cost and mass constraints, it's not practical to bring material to the moon, but it would be so much better to use moon material itself, in situ material, to protect the astronauts itself. So an emerging idea would be using the moon sand and the moon regolith as shielding itself. To do that, we need to anyway characterize this material and be able to predict what would radiation do when interacting with this big wall of moon sand. And we are also studying this kind of interaction. For this, we produce for us big amounts of moon sand. This moon sand is produced based on the composition of the real moon that was taken from samples of the Apollo mission. So we can have a proper atomic and nuclear composition of the sand as it's on the moon, and then we can scale it up in production for very big targets and use it for looking at what happens when we radiate with this moon, how much do we need, does it help, and could we eventually think of this strategy for protecting the astronauts.
Kako bi se uspješno razvile ove strategije, rade se različite istraživačke studije na osnovu eksperimenata u kojima ključnu ulogu ima galaktički simulator kosmičkih zraka. Ovo impresivno postrojenje generiše spektar snopova teških jona kojima se na Zemlji u eksperimentalnim uslovima simulira zračenje koje postoji u kosmosu. U centru GSI u Darmstadtu različite grupe naučnika koriste galaktički simulator kosmičkih zraka, a vode se mnoga istraživanja koji imaju u fokusu zdravlje kosmonauta. What are the main factors that can impact astronauts' health in deep space?
So here at GSI we are indeed one of the unique ground-based facilities for deep space research. There are a couple of other facilities in the world who can mimic the radiation in space. But at this facility specifically, we can reach energies and intensities that cannot be reached anywhere else, except for the Brookhaven National Laboratory. The NASA facility has a similar setup to GSI. They already have a galactic cosmic ray simulator, and this is something that we have in the pipeline here at GSI. So in 2024, we will do the first commissioning tests. And then hopefully this will be available for users from all over the world to come and do their ground-based experiments over here. These ground-based experiments are quite important because the astronaut pool that has been in space is very small. Normally there are only a few astronauts in the space station at the same time. So the reason why the experiments that we perform here on Earth are so important is because the pool of astronauts that we have that has been in space is very limited. We mainly have male astronauts from the previous studies, and the follow-up that you need to observe the health effects needs to be quite long. So we don't know that much at this stage. This is one of the problems, so this is why we prefer to do ground-based experiments with cells and animals in order to mimic what can happen in space. Another advantage is that we can specifically focus on space radiation. If an astronaut is in space, this astronaut is exposed to multiple stressors. So it's radiation, it's microgravity, it's a confined environment, isolation. So there are many factors that can impact an astronaut's health. Here at GSI, we can focus specifically on radiation, and that we can add some of the other stressors to the experiments as well. But you have possibility to disentangle the stressors that eventually cause the health effects that we observe, or that we could observe. On top of that, if we go in deep space, which is on the roadmaps of most of the space agencies and also private companies these days, that we go beyond ISS, so to the Moon and Mars, we leave the protective magnetosphere of the Earth, so we are exposed to a completely new type of radiation that we have never faced before, except for the few moon missions we had so far. But yeah, we really plan to send more and more people into deep space beyond this barrier. So this is why, we urgently need to have more information on the health risks. At the moment, space radiation remains one of the main showstoppers to make the Mars mission possible.
What has been known so far, and what are, so to say, the open topics in this field?
Yes, there are many open topics. For sure, we know, for instance, that stressors like microgravity affect the immune system of astronauts. These things are known because we could study the blood samples of astronauts in space. When it comes down to radiation, it's not so clear because the levels in space are also very different from what we encounter here on Earth. So it's a low dose and a low dose rate, meaning that it's the portions of radiation that you receive are much smaller than an acute exposure that, for instance, happened during the atomic bombs here on Earth. Unfortunately, that is one of the biggest populations we have from an epidemiological point of view these days. So the health effects that are currently receiving the main attention of the space agencies was cancer risks for a very long time. There is a risk that an astronaut might develop leukemia on the Mars mission because at the moment the mission will take 3 years. Leukemia risks can happen relatively early after exposure. This is what we've seen with the atomic bomb survivors, for instance. But also cardiovascular diseases, neurodegenerative diseases, and this is also, the last one is definitely also a problem when the astronauts return. If the cognitive function and the behavior is affected, then it could potentially maybe enhance Alzheimer's risks and other neurodegenerative effects when they return to Earth. And of course we want to prevent that too. If it would happen in space, that they have cognitive problems, it can really impact the mission safety. So these are definitely the main health effects that at the moment are getting attention.
Once scientists identify these risks, they start looking for countermeasures to mitigate them. So what is currently going on in this context?
There are different strategies. You can potentially do drug development, like this is also one of the focuses in our microbiome project, where we want to find, for instance, metabolites or specific signatures, biomarkers that we can use to develop drugs in the future. But of course, one of the main points of attention is the shielding. So of course you want to protect that. That would be the first step, that you try to protect an astronaut from the radiation that is coming from deep space. And this you can do through shielding. Of course, it brings some challenges because we are limited to what we can send in space. Here on Earth, like our accelerators are surrounded by layers of concrete. This is impossible to mimic in space because it's just too heavy and bulky to bring there. So at the moment, a lot of companies are investigating how we can, for instance, the material where the spacecraft is made of, and the vehicles that astronauts might use on the Moon and Mars, what would be the best material to build these pieces of equipment from. And on the Moon specifically, for the Moon base, a lot of people are putting resources into the Moon regolith, which is the dust that you can find on the Moon. It's basically, it's like sand, so the idea would maybe be to build a Moon base out of the sand that we can find there. So if we can use this as a building material and maybe even put the Moon base partly underground, that could be one of the best shielding options we can have in space. But of course, the material is unknown on Earth. I mean, there are samples that came from the Moon which we can investigate. We can even try to replicate it or something that comes really close to Moon regolith. And then by testing how thick these bases should be, these are also part of the experiments that are happening here at GSI.
You mentioned moon sand. How was it replicated?
The chemical composition is known, so there are universities and companies who really study these. So by analyzing the chemical composition of the Moon regolith, you can try to find a material on Earth that can represent this. So I think this is what is mainly used in the experiments that we do here, because of course this Moon regolith is precious and we don't have very high volumes of it. So this is at the moment what is in use. So once we have the GCR simulator up and running, this will be one of the first projects we will do, is to test different shielding material. Moon regolith might be one of them, but also really the material of the spacecraft, because there have been studies showing that simulation studies showing that the thicker the shielding, it could also create an additional problem that more secondary radiation is created. And that secondary radiation, for instance, contains neutrons, and neutrons have a very high biological effectiveness, so they might actually be more harmful for the astronauts. So the idea of these experiments is to find the balance, like what is the best balance, the thickness in shielding and the health effects. So this is, in one of the first experiments, we will expose cells in a first instance, in a later stage also animals, to look at the cognitive function, the impact on the brain. But in the first instance it will be cells, just to see how the DNA of the cells is damaged after the radiation exposure, and if the cells, what would be the best thickness. It's a first starting point.
Let's say that you use a galactic cosmic rays simulator in your experiments. So what is it, and how do you use it?
So the GCR simulator is actually a modulator that we put in our beamline, and the word says it modulates or it kind of recreates the spectrum of radiation that we encounter in space. So in most of the facilities, and up until now, also here at GSI, we have been limited to single ion experiments. So in our case, iron ions are mainly used for the space studies because this is the most abundant particle in space. But of course, when astronauts are in space, it's a much more complex environment. It's not a single ion exposure, but there are many types of ions. So based on the measurements that have already been performed in space, we kind of know how the spectrum should look like. And based on that, we built a GCR simulator here at GSI that can mimic that complex environment. And this will be done by modulating the beam in such a way. We will use different beam energies, and this modulator will then eventually, at a location where the cells or the animals or the dosimeter, whatever you use in your experiment, is located, it will mimic the space environment, the deep space environment, in a very reproductive way. And we will also have the possibility to mimic different scenarios. So to, for instance, mimic what happens at the Mars surface, what happens in transit to Mars, what happens on the Moon, because the radiation spectrum is very different in the different locations in space.
Scientists in your group have also been working on the microbiome project. What is the aim of this research?
the idea of the microbiome project is that we try to find a biomarker for space radiation risks, because of course you can have physical dosimetry in space. You can send a dosimeter on board of ISS, which can measure the radiation in a very efficient way. Of course, to translate that to a health effect is very difficult. So we are actually looking for a biomarker, which is a signature that you can find in the body of an astronaut, to predict what the health effects will be, or to confirm what the health effects will be. But in our case, it would mainly be to predict what will come after the radiation exposure. So this biomarker will give us the possibility to maybe link this to cancer risks, but also maybe due to the gut-brain barrier, the risk of cognitive effects, the risk of immune effects. So because the microbiome is connected to every part of our body, it's very interesting to start from there. Also, collecting the samples is not that complicated because you work with fecal samples, so it's not so invasive. And in this project, we look for dysbiosis, and this means that the microbiome is normally balanced. All these microorganisms live happily together when everything is balanced out. But for instance, due to radiation exposure, this composition might change. And once you have a dysbiosis or a change in the composition, it will create a health effect, or it can create a health effect. And this is what we will try to observe by irradiating animals with this predisposition for colorectal cancer. And if we see, we hope to see that shifts in the microbiome will also be observed with differences in the cancer risks. And this is how we could potentially lay the puzzle and see how it can be used in the future in astronauts.
So we'll use the gut microbiome of a mice model. So the mice model will have a genetic mutation to develop colorectal cancer or gastrointestinal tract cancers at an earlier stage during their lifespan, and then we'll use this to understand how the gut microbiome changes in its functionality, diversity, and composition to unravel a biomarker that can be linked to microbiome and space radiation risk, just to further develop maybe a countermeasure that astronauts can take to consume maybe as a probiotic, as food, or as a drug, to prevent them to develop colorectal cancer when going to a space mission.
Ova složena istraživanja veoma su značajna jer je mikrobiom jedan od temelja ljudskog zdravlja. Mikrobiom je skup svih mikroorganizama u našem tijelu. To su trilioni bakterija, gljivica, virusa i ostalih mikroba koji kada su u ravnoteži proizvode zdravlje u našem sistemu. Njihova neravnoteža obično je podloga za brojne zdravstvene rizike i bolesti poput sindroma nervoznih crijeva, raznih tipova kancera, poremećaja u radu imunog sistema. Na ove teme u centru GSI rade se razni eksperimenti, a u posebnom istraživačkom fokusu su rizici od dobijanja kancera.
So we'll have a mice model which has a genetically modified gene, which is the APC gene, which is found mostly in colorectal cancer. And then this mice will have a predisposition to develop colorectal cancer. So we will house them here at GSI, and then they will just do their normal healthy living, and then we'll, at a certain point in time, we'll irradiate them with either X-rays as a baseline, and then further go into iron ions by using the GCR simulator, so Galactic Cosmic Ray Simulator. And then we'll just continue to collect before irradiation and after irradiation fecal samples, and then till a point where we'll say, okay, we'll terminate the experiment and then do the analysis of the fecal samples by doing DNA extraction and continue with omics data analysis. Further on, if we can understand what is the specific biomarker that we found in the gut to maybe prevent cancer formation in the mice, we can use this and develop maybe drugs or a probiotic that astronauts can consume when they're on the ISS, or even further when they go to a mission on the Mars or Moon, to consume this and then prevent them from having dysbiosis, which is the imbalance in the gut, and also developing cancer in the gastrointestinal tract.
Kancer je jedna od najizazovnijih istraživačkih tema našeg vremena. Mnoge generacije naučnika decenijama sklapaju kockice istraživačkog mozaika, pokušavajući da dođu do konačnog i sveobuhvatnog odgovora na pitanje kako izliječiti ovu bolest. Kancer je i cijena koju bi za svoje svemirske misije mogle platiti mnoge generacije astronauta.
You have dedicated your research to both cancer and helping deep space studies. How does it feel for a scientist to contribute in this field?
Yeah, I mean, it maybe comes back to the question like how we all ended up in doing what we're doing right now, right? I think most of us have family members or people around us that are affected by cancer. In my case specifically, this was my mother when I was in high school. So this is definitely a trigger. Then later on, when I was at university, I lost a very dear friend at the age of 28, which was quite unexpected. Also to a breast cancer. So I think this is probably the intrinsic personal motivation to go into science and cancer research. How we link that to space, this is sometimes for me difficult to answer because I always did cancer research before I moved to GSI. But the nice thing about space research is that it has so much applications on Earth as well. It's an accelerator. Well, we work in an accelerator facility, but the space environment is an accelerator for technology, for developments, also related to health, which we might not find when we just stay in our labs on Earth. So I think by putting a lot of efforts and energies and understanding what happens in space, we learn so much, because in space, for instance, astronauts age much more rapidly than we do on Earth. And aging is a huge problem of our time. I mean, population gets bigger, people grow older, and cancer is also increasing with age, of course. So I think this is for us, yeah, there is so much we can learn by doing this research, and I think its applications on Earth should not be underestimated.
What are the applications on Earth you are referring to?
So if you think of an example, for instance, is that if we could find, for instance, a biomarker in the microbiome and develop a probiotic or a strategy to mitigate the risk, this is something that could be applicable to a lot of people on Earth as well. For instance, if you have cancer patients that have to receive treatment, it might also be a better way to protect the gastrointestinal system from the radiotherapy effects. And next to that, if it could really be used as a way to prevent cancer development, I mean, the applications are even much larger. So yeah, in this specific project, that would be one of the direct applications. But I think one of the most interesting applications for me, for instance, it's not directly linked to radiation, but for instance, when astronauts go to the ISS, because of the microgravity, the brain is also changing, and they at the very beginning it can happen that they lose the sight of depth, so they really have to learn again how to grab a glass, how to grab a pen to write and things like that, and by studying which parts of your brain are activated to learn these sort of things again from scratch, it can help us a lot to really help people who are born with predispositions for this or with problems who lack this cognitive function. So these are some of the examples, for instance, how space can help us to really find solutions for problems on Earth.
GSI is the biggest center of its kind in Europe. It is often called a talent factory as it attracts so many young scientists from all over the world. So how does a facility like this accelerate the development of young talent?
Yeah, for me there are multiple parts or answers to this question. I think for sure the technology is unique. So it gives you access to facilities that are very unique to GSI. And that attracts talent, of course. You are able to work with a very, with a unique population of people who are really, really keen to make new discoveries, to give the best of themselves, to make use of this fantastic facility. Next to that, I think for me a very important factor is that it's very international. It's very diverse as well, which I personally, as a scientist, appreciate a lot. I think we can also learn so much from one another. And sometimes coming from a different background or from a different country or a different field of research, because it's also very interdisciplinary. I am, for instance, a biomedical scientist, but yeah, I share the office with an engineer. So we have completely different backgrounds, but it also fosters, well, very nice discussions, and you can find solutions for problems which you sometimes wouldn't find if you just stay in your own environment. So I think the interdisciplinary part and the diversity are really key to a facility as GSI and are part of its success, I think.